All right. We know that a chord is a segment that connects two endpoints on the circle. A diameter is a chord of a circle, okay? A diameter is a chord that passes through the center. So if the center of my circle is right there, that would be a diameter. But it's still a chord because both endpoints are on the circle. Some chords are longer, some chords are shorter. In fact, the longest one is going to be the diameter. Anything that is a diameter is a longest chord of the circle. And the further it gets from the center of the circle, what happens to the chord? It gets shorter, okay? So the closer we get to the center, the longer the chord is. The further from the center, the shorter. It's a pretty simple relationship. Is a radius a chord, by the way? No, because a radius doesn't have both endpoints on the circle. A radius has one point at the center of the circle. Chord has to have both endpoints on the circle. So, some chords are longer, some chords are shorter. We're going to kind of take a look at that relationship today, essentially. Basically, here's what it comes down to. We've got a little sketch pad here that demonstrates it. With measurement. And we already kind of looked at this intuitively, but we can look at it with measurement. That A is the center of my circle. Notice that when my chord actually goes through A, the distance center is 0. The length of the chord is 14.7. That's the diameter of the circle. And as my chord gets further from the center, it gets shorter. Okay? In fact, when my chord gets to be a length of 0, or almost 0, because of rounding here, it's 7.4 centimeters is the distance to the center, which would be the radius of the circle, which is half of that. So, okay? So we get the idea that the shorter the chord is, the further it is from the center of the circle. The closer it is to the center of the circle, the longer the chord is. What if two chords are the same length? What does that tell you about their distances from the center of the circle? They have to be equally distant from the center of the circle. Or if two chords are equally distant from the center of the circle, it would also tell us that they have to have the same length. And really a lot of this comes, folks, from triangles. Oh, that's right. I'm on Sketchpad, not on Smartboard. Can't do that. But a lot of this comes from triangles. Oh. Okay. Yeah. It's not going to be me. Let's put it that way. All right. So, how do we know if chords are congruent? Two chords are congruent if they have the same length and they lie in the same circle or congruent circles. Now, this is a little different from congruence that we've dealt with in the past. Congruence always meant same length, same measurement. Now, we have to have the same measurement and either be in the same circle or in congruent circles. Two circles are congruent if they have the same radius. So just because two chords have the same length doesn't mean they're congruent if they're in different circles of different sizes. It's a little weird, but it's the way it works. Also, congruent chords create congruent arcs. Now, we haven't talked about arcs much yet. We'll talk about them in the second half or in the third part of Unit I. We have actually 4 parts in Unit I. But those would be the arcs. So arc AB and arc CD are the same if chord AB and chord CD are the same and vice versa. You say that's about the only mention of arcs we get so far, but that's a true fact about chords. A lot of the problems we deal with are very, very basic. If this is the center of my circle and these distances are equal, what has to be true about these two chords? They have to be congruent, so we just set them equal to each other. The same thing we've been doing all year long. Okay? And by the way, when I measure the distance from a point to a line, remember that we always measure the right angle distance. So when we measure that distance, we're always forming a right angle, which means we have right triangles. When I draw the radius in here, Okay. And guess what? These two triangles have to be congruent because of hypotenuse. The radius is the hypotenuse of both of them. That's a constant. They're congruent triangles by hypotenuse leg, which means these triangles are also, all four triangles are congruent. Oh yeah, lots of fun stuff going on here. We never have a shortage of triangles because you can never go very far without coming back to triangles. This is an interesting one. If one chord is the perpendicular bisector of another chord, and the chord doing the bisecting is the diameter of the circle. And you're probably thinking, okay, among the list of useless information, this is high up there at this point. But actually, this one is extremely useful. Let's just go over it again. One chord, the longer chord here, is a perpendicular bisector of the other. So the chord doing the bisecting must be a diameter of the circle. Now, what's critical about the diameter of a circle? What is on the diameter? The center of the circle is somewhere on the diameter. So when I do this with just one chord and find its perpendicular bisector, that's not really that interesting. But what if I put a second chord in here? And then found the perpendicular bisector of that chord. What happens where the two diameters intersect? What have we just found? The center of our circle, haven't we? So this is a way, if I don't have a full circle, if I just have a partial circle, to actually find where the center of the circle actually lies. You're still thinking, okay, still pretty high up on the list of useless information. Maybe so. Until search and rescue. This is actually a geometry theorem that gets used in search and rescue all the time. If something doesn't have a GPS transponder but just has an emergency beacon, that beacon signal generally goes out in a spherical pattern, or essentially a circular pattern, right? So let's say it's an avalanche deal. And someone's got an avalanche beacon on them. They don't have a GPS transmitter, but they have a beacon. What do? The search and rescue people come on, they find where they start hearing the signal, they mark the spot in the snow. They walk in a straight line until they lose the signal, they mark that spot in the snow. That is a chord of the circle from the signal. Okay? They then find the center of that distance, so find the middle, and then mark a perpendicular line along that. They know that's the diameter of the circle. They then do it again. Another searcher will do the same thing over here. Okay, find the two signals, find the center, and mark that along. When they do that, they find where those two diameters intersect. That's where they dig for the buried avalanche victim. Quite honestly, before GPS transmitters, which is probably less than 20 years ago, this was the only way that they found people who were, when you went into an avalanche area, you had to carry a beacon that would transmit a signal. This is the only way they were able to find them without a GPS style transmitter. GPS makes it a little better, but they actually, GPS, if the signal is blocked because they're buried in snow, doesn't work so good. GPS needs a clear line of sight to the satellite. I mean, you know that in your car. If you have a GPS in your car and you put it in the center of your car, it doesn't work so good. It has to have some line of sight to the satellite to receive signal. So if someone's buried in snow to this day, even having a GPS transmitter is limited in its usefulness. A lot of times they still have this beacon and they have to find this way. Or think about that missing plane right now. There are all sorts of transponders sending out pinging signals, supposedly. If they could find that signal in a couple of spots where they find and lose that signal, they can very quickly locate the plane using this exact technique. That's when one chord is a perpendicular bisector of the other, we can find two of those, we find the center of our circle, we know exactly where our object is we're looking for. So maybe if you're never going to be, carrying an emergency transponder, it still is up there on the list of useless information. But you never know. Actual real application of the geometry principle. How about that? Woohoo, put this day on the calendar. When your parents ask you what you learned in school day, hey, we learned how they did search and rescue for people stuck in airlines. Yeah. Right. Well, you know what happens if you happen to be at a place where someone's buried and you want to go help? Wouldn't you like to be a helper? If someone was in trouble and in need, wouldn't you want the ability to be a helper? Well, I'm thinking maybe you would want to help and help that person get found and save their life. It's just a hobby. It's not an occupation. It's a hobby. Yeah. All right. All right, and this is just kind of a draw, two-picture doing it. John and Fred are searching for the avalanche victim. Okay. So as we're looking at this sort of thing, what kind of problems can you expect in the homework tonight? Circle, setting things equal to each other. Yeah, it's really not that difficult. I think you'll find tonight's homework is actually very, very, very straightforward. The worst you might have to do is solve the right triangle again. Yep. On page 667, I think you'll be fine. So I'll put the assignment on the board. Look who's talking. Did you really just tell someone else they have issues? Because they do. You got the whole subscription. They may have issues. You've got a subscription. Well, I'm not denying it. Not for a second.